Hello friends, so today we are going to discuss 3 questions from statics. Okay, 1 second. Yeah, and so in the first question it is given that a stick of linear mass density lambda rests against a circle of radius r. The stick makes an angle theta with the horizontal and is tangent to the circle at its upper end. Friction acts at every point on the contact and it is assumed to be sufficiently large to keep the system in static equilibrium. Determine the friction force exerted between the ground and the circle. So we can, as per the question, we can just draw the basic figure. So we are given a circle and it is resting on a ground and its radius is given as r, and there is a stick which is inclined and is tangent to the circle. So it is tangent to the circle, so let me draw properly. So this is a tangent to the circle and making an angle of theta with the horizontal. And we have to find out the frictional force exerted between the ground and the circle. Okay, so this is the basic question. And so the various forces that will be acting in this system will be, first one we can say will be our normal at the point of contact of our stick and the circle, and there will be a frictional force. Let us call this as our f of t, and there is a frictional force between the ground and the circle. Let us call this as f of f. And if we join this to the center of the circle, then the angle will be divided into 2 parts, that will be theta pi by 2 and theta by 2 as well as theta by 2. And along with this later on we can just divide. There will be also a mg acting on it, okay, and that for that we can come later on. Okay. So first of all, and L is the length of the stick. Okay, so mg will be acting somewhere here, the downward direction, and it will be at a distance of L by 2 on the vertex. Okay, and let us call this as our A, this point as P, and this is our B. And it is also mentioned this entire system is in static equilibrium. Okay, so we have to keep focus on this. And first of all, let's find out what will be the relationship between the friction between the circle and the ground and the friction between this stick as well as the circle. And for the sake of simplicity, let me draw this again. So we are going to have a friction, that is our, and other friction which is along the stick, and we call this as a tangential friction for the sake of simplicity. And so this is center, and it will be at a distance r, and this will be also at a distance r. Okay. And we have to remember that this circle should be in static equilibrium. Okay. So we can say for the circle to be in static equilibrium, the torque produced by the tangential friction and the friction between this circle and ground should be equal. Okay, they should balance out. Okay. Therefore, we can say that a torque about the center of the circle, let us call this as C. Okay. So you can say torque about the center of circle due to our tangential friction and friction between the stick and the ground must be equal. Or in terms of equation, we can write torque because of our tangential friction should be equal to torque because of our other friction. And torque we know is force into lever arm. So first force, tangential force, is our F of t, which that is frictional force. Lever arm is our R, and other side is also lever arm is our R. So this R and R cancels out. Therefore, from here we get that the friction between the stick and the circle is equal to friction between the circle as well as the ground. Okay. So it means these two values of the friction are equal. Okay. And so this is the first part. And in the second part, let us, you can say, find out the balance equation or equilibrium condition for the stick also. Okay. So we know that our stick is somewhat like this, and it is making an angle of theta. So this is our A and this is our B, and L is the length of the stick. So at the point of contact between the circle and the stick, there will be normal acting. So let us call this as well normal N, and there will be also a mg because of the stick's weight. So this will be over mg, and mg will be at a distance of the midpoint of the stick, that is L by 2. Therefore, this distance will be coming as our L by 2 cos of theta. Okay. Therefore, we can say that our moment balance for stick so we have our weight, that is our mg, and we can write this as our mg L by 2 cos of theta, and then we are having a normal, that is our N, and that is our N multiplied lever arm, that is our L. And these two should be, you can say, they should be equal. So we can say for equilibrium, we can write that our mg L by 2 cos of theta should be equal to N multiplied by L. And this L and L cancels out. From here we get that the value of the normal is equal to our mg by 2 cos of theta. So this is the value of the normal. And now we come to the horizontal equilibrium of the circle. So we can say horizontal equilibrium of the circle. So let us draw the circle first, then we can draw all the forces. So this is our circle, and we have a stick, it's our ground, and we have a stick which is tangent to this circle, so it is somewhere here, and making an angle of theta. So the stick will be, there will be normal because of the stick towards the on the circle. So this is our normal N, and we can divide this into two components. So this angle will be over theta. So we can say this will be over N sine of theta, and we get this N cos of theta. And we are also going to have a friction. Like I said, the friction will be along the stick, and we can further divide this also into two components. And other one will be in this direction. So this angle will be over theta. So we get this as our f of t cos of theta, and this will be f of t sine of theta. Okay. And the horizontal is our friction in this direction, which we called as a f of f. So these are the forces acting on this. Okay. And so we can write that for the horizontal equilibrium of the circle, we can write the equation that our N sine of theta will be equal to over f of f plus f of t cos of theta. And we calculated, we have found out that our f of t and f of f are equal to each other. Therefore, we can write that our N sine of theta is equal to f of f 1 plus cos of theta. And from here we can say the friction between the circle and the ground, that f of f is equal to over N sine of theta 1 plus cos of theta. And also there will be mg in the downward direction, but that is not required. We are only talking about the horizontal motion, because vertically there is no as such motion in this. And So this is our value of the friction, and value of the normal we already know, mg by 2 cos of theta. So we substitute it, we get this as our friction is equal to, this comes as mg by 2, and we can write this as our sine of theta times cos of theta 1 plus cos of theta. And our and we can let me redraw this figure, only the triangular part. So this is our point, this was our point A, this was B, P, and this was our B, and this was center C. So this is A, and this is A, B, P, and this is center C. So let me join this also, and if I join my AC, okay, so total angle was theta, so each angle will be our theta by 2 as well as our theta by 2, and this is our length, our L, and R is the radius. Therefore we can, from this we can write that our L is equal to R upon tangent of theta by 2, and if m is our total mass, therefore we can say m is equal to mass density multiplied by total length L. Okay. And so here we are interested in finding out, okay, let me write it here. So we have our L is equal to R upon tangent of theta by 2, sorry, and this theta by 2, tangent theta by 2 rather, can be used for the trigonometric identity, and we can write that our L is equal to R, and this comes as 1 plus cos of theta, and this comes as our sine of theta. And now we can write the mass equation, that our mass is equal to, it is lambda times L, so this comes lambda R, and we have this as 1 plus cos of theta and our sine of theta, and we substitute in this equation. Okay. Therefore we get that our frictional force will be equal to our lambda R 1 plus cos of theta sine of theta times g upon 2. We have this as a sine of theta cos of theta and 1 plus cos of theta, and this 1 plus cos theta, 1 plus cos theta, sine theta and sine theta cancels out. Therefore we get that the frictional force between the circle and the ground will be equal to, this will be our lambda rg 2, and we are left with cos of theta. Okay. So this is our frictional force between the ground and the circle, which was asked in the question. Okay. And next question. Okay, this question is somewhat similar to the first one, but here the arrangement is you can say made n times. Okay, so let me go through the question first. A large number of identical sticks, each of linear mass density lambda, and identical circles, each of radius r, are arranged so that they alternately lean on one another. Each sticks make an angle theta with the horizontal and is tangent to the circle at its upper end. These sticks are hinged to the ground and all other contact surfaces are frictionless, in contrast to the previous problem. Okay, previous problem is the first one which we discussed. In the limit of infinite sequence of sticks and circles, determine the normal between a stick and the circle on which it rests, far to the right of the system. Assume the final circle is supported by a vertical wall to prevent the motion. So entire system is in equilibrium. Okay, and so let me draw the figure. So we have, this is suppose our first circle, and this is our second circle, and this is our third circle, and it is going on so on, and they are rest on a plane surface. They rest on a plane surface. So let me and there is our stick which are acting tangent to these circles. So this is a first stick, and there is a second stick. The second stick touches the first one and then acts as a tangent to the second one. Similarly for the next part also, and the angle between them is our theta. Okay, please remember all these sticks are of same length. Okay, the figure is not up to the scale, but all these sticks are of the same length. And the circle, each circle is having radius r. Okay, so this question is somewhat related to the previous one, but here we have arranged same sequence repeatedly towards the right. So this is the major difference. And so first of all, we are going to draw all the relative or the necessary forces. Okay, for that we are going to consider only two circles, and based on this we can just discuss the entire geometry, because that will be repetitive in nature. So suppose this is our first circle, and it is lying on a surface, and there is also a second circle, and second circle we will draw only partial one because that is not much required. And then there is a stick which goes something like this, and similarly to this part also. And we are given that, let us suppose this is the center. So we are going to have this will have a radius r, and to this end also we have a radius r. Okay. So let us consider this our circle C of I. So next circle will be C of I plus 1, next will be C of I1 plus 2 plus 3 plus 4 continuously. And let us suppose this is center C, and this is our A, this point is our B, and this is our P. Okay, and let us join this our AC. So obviously we are going to get theta by 2 as well as our theta by 2. Okay. And on the other side also, if we join our, we can just, because of the symmetry it will be coming like this, and if we join, so this angle will be also our theta by 2, and this will be also our theta by 2. And there will be a normal that will be acting at this point. Okay, so let me draw the normal. So this is normal, and we call this a normal as n of I, and there will normal here also. Let us call this normal as our n of I plus 1. Okay. And L is our length. Okay, and here also this is AB, and let us call this as our X, and this is Y. So XY length as well as AB length is same, they are of L length. Okay. So let me put it here separately. AB is equal to our XY is equal to length L. Okay. In figure it looks little bit smaller and bigger, but they are having of equal length, so we have to keep this in mind. And for the sake of convenience, let us assume this AB is our first stick. We call this as our S of I, and XY is our second stick, so we are calling this AB as our S of I, and our XY we are calling this stick I plus 1. Okay, so we are calling this stick I plus 1. And okay, so in the first question, which we did, we proved that our this length and our radius r, because this will be over 90 degree. Okay, so we can write that our L is equal to r tangent of theta by 2. Okay, we already proved it, or we can say from trigonometric identity we can also solve it. Okay. And for the sake of convenience, we are going to assume that let this tangent of theta by 2 is called as our t. Therefore, we can say that our L is equal to r upon t, because this tangent of theta will be used multiple times. Okay, so we are going to replace it by a single variable, that is our t. And we can also find out the mass. So mass is our m, which is lambda times L, and it comes as lambda r upon t. Okay. And so let us find out, this is our xy, and this is b, and this is, let us call this point as our O. And so in this case, we are going to find out that the fraction of the stick, how the xy, because it will be divided into two parts, xo and xy. Okay, so we are going to find out the fraction, what is between these two. Okay. And the hinge is our nothing but our x. So this is our hinge. Okay, which we are going to discuss. A is also hinge, but we are going to discuss our with respect to xy stick and replicate it to our AB. Okay. Therefore, we can say that our the stick length xy is in terms of xy in terms of fraction, in terms of fraction, in terms of fraction from hinge to contact point. And let us call that fraction as our alpha. So alpha will be equal to the total length of our so we can measure this length, and this length will be our r tangent of theta by 2. And therefore we can see that our r tangent of theta by 2, total length is our L, and tan theta by 2 is our t, so we can write this as r of t, and our L we can write as our r upon t, so this comes as our t square. Okay, 1 second. Yes, okay, so this L length is our r tangent theta by 2, but here the fraction, that is our xo, is our r tangent of theta. Okay, so we found out the fraction in terms of our, that is of alpha, which is equal to our t square. Okay. And therefore we can say, or let me draw the figure and then we can all further sort it out. So we are going to draw our xy on the larger scale. So this is our x and y, and suppose this is our center C, and there will be a normal. Okay, it doesn't look like a normal, so let me draw. This is stick xy. Okay. And this is our base, this is our P point x, and this is our O point. Okay. And if we join this also, so total angle was theta, so this will be coming as theta by 2, and this also our theta by 2, and the normal is at this position, which we called as our n of I, and there was other normal at y, which we called as n of I plus 1, because of the second circle. Okay, here this was the normal because of the circle ci plus 1. And so here this is angle theta, and there will be a weight mg in the downward direction, and let me suppose it is somewhere here, so we get this is our mg. Okay. And this distance obviously will be equal to L by 2. Okay. And this our xo we just found out is our r tangent of theta by 2. Okay. Therefore the distance up till here is our r tangent of theta by 2. So let us use, you can say, the torque with respect to over x. So we can say that our torque about the hinge, and hinge we have taken here x. So first of all we have our mg, so we have our weight, let us call this a tau mg or tau g for the simplicity, and tau g will be equal to our mg, and this distance will be our L by 2 cos of theta. So we get this as our L by 2 cos of theta. And then will be normal our n of I. So we have our n of I, and this n of I, let write this as what tau n of I will be equal to r tangent of theta, but r tangent of theta by 2, and that is nothing but equal to our at a distance of r tangent, okay, we can solve this r tangent of theta. So we can write this as r tangent of theta will be equal to our rt, because tangent of theta by 2 is our t, and our r is equal to our lt. So we can say this is our L t square. So in place of r tangent theta by 2, we can write L t square. Therefore, we get this will be equal to our L t square multiplied by our n of I. And finally, we are having normal of n of I plus 1, that is torque because of n of I plus 1, and the total distance is our lever arm is of L, and multiply by I plus 1. Now everything is in equilibrium. Therefore, we can write for equilibrium, we can say that our torque because of our Ni plus 1 will be torque because of our Ni plus torque because of our mg. And now we can simply substitute their values. N plus y is our L times I plus 1, and then we are having our n of I L t square plus mg by 2L cos of theta, and we can just sort out our L. Therefore, we get that our n of I plus 1 will be equal to mg by 2 cos of theta plus t square n of I. So this, we can treat this equation as a general equation for our normal. Okay. And if we substitute value of our 1, 2, 3 and 4, we are going to get all the values. Okay. So let us solve it as a recursion problem, or we can say finite sum expression. Recursion, or we can say this as our finite sum problem. So if we put I is equal to 0, so we are going to get this first part. Okay, we have to remember that we solved everything with respect over this x and y, and for this we assume that it is our I plus 1. So here we can say this is our I plus 0. Okay. So therefore we are going to put that our n of 1 will be equal to our mg by 2 cos of theta, and we can put our to n of 2. So n of 2 will be equal to our mg by 2 cos of theta plus t square and n of 1. Okay, so for this value of I was 0, for this value of I is equal to 1. So we are going to solve this second equation, and this gives us, we substitute here n of 1, therefore we get that our n of 2 is equal to mg by 2 we can take as common along with the cos of theta. So we can say mg cos of theta divided by 2, and it comes as 1 plus t square. Similarly, we can solve other part also, like we get n3 will be giving us mg cos of theta divided by 2, and this comes as 1 plus t square and t raised to power 4. So in general, we can write this as our n of I will be equal to mg by 2 cos of theta summation k to 0, and here we have I minus 1 t 2 raised to power k. Okay. So this is our expression for this, general expression for all these normals, n of 1, n of 2, n of 3, n of 4, n of 5, likewise. So it will be going up till infinity. Okay. So this is our general expression, and therefore now we can use the convergence, or we can say the geometric sum convergence. So we are interested in only this portion. Okay. And we can write that if our theta is less than pi by 2 but greater than 0, so this gives us that our t will be less than 1 but greater than 0. Therefore, we can say that our summation k 0 to infinity t raised to power 2k will be equal to 1 minus t square. So this is a general expression for this, the series. Okay. And we have to solve it up to infinity, so we are going to use the limit concept. So we can say limiting normal for entire chain, and therefore we can write our n is equal to limit I tends to infinity, and this is our n of I. So from here we get this is our mg upon 2 cos of theta and 1 minus t square. Okay. And now most of the things are done. We only going to substitute some relationships, and like we know that our m is equal to lambda times L, and our L is equal to R upon T. Therefore, we can say that our normal is equal to, now in place of mass, we can write this as our lambda L g upon 2, and this comes as our cos of theta 1 minus t square. And our length we can substitute in terms of radius. So we get our normal is equal to, this is our lambda g by 2 r upon t, and we have cos of theta 1 minus t square. And there are various ways in which we can write the equation. we can further solve it. And if we substitute value of t, t was our nothing but tangent theta by 2. Okay, so we have to remember we have taken t is equal to tangent theta by 2. So we can further substitute tangent theta by 2, convert this half angle into sine and cos, and further solve it. Okay, so we can treat this as our final answer. That depends upon if you want to substitute value of t, we can use the value of t also. Okay. And next question. It states that a spool consists of inner axle of radius r and an outer circular rim of radius capital R, which rolls on a horizontal surface. A thread is wound throughout around the axle and is pulled with a tension T at an angle theta above the horizontal. So based on this, we have three questions. First is, for a given values of small r and capital R, determine the angle theta for which spool remains stationary. Assume that the friction between the spool and the ground is sufficiently large to prevent slipping. Part B, for given r, small r and the coefficient of friction mu between the spool and the ground, find the maximum tension T for which spool stays at rest. And finally part C, for a given r and mu, determine the value of small r that minimizes the maximum allowable tension from part B. In other words, find the axle radius r that makes the spool slip under the smallest possible applied tension T. What is the minimum value of T? Okay, so these questions parts look a little bit lengthy, but they are very easy to solve. Okay. So first of all, let's draw the basic figure. So we are given that we have a spool. This is inner and this is our outer, and this is our ground. So we have an inner radius small r and we have our outer radius is capital R, and the thread is wound on our inner one and it is pulled by tension T, which is making an angle of theta with the horizontal. Okay. So this is the basic question or basic figure. Okay. And so let us call this contact point as our P and this our P prime. So we can divide this tension into two components. So this is our point P, this angle theta. So we can say we get this as our T cos of theta and we get this as our T sin of theta. Okay. And suppose this is center C. So center C is somewhere here. So, and this is our P prime. So we are going to have our mg in the downward direction, and there will be a force of friction. Let us suppose that is of F, and there will be also normal acting upward direction. Okay, so for the time being, these forces will be sufficient. Later on, if required, we can use more forces. And so we are going to solve part A. And for our horizontal equilibrium, we can write that our horizontal equations, we can write, because everything is equilibrium, so we can say F minus T cos of theta is equal to 0, which is that F is equal to T cos of theta. And then we have a vertical equation. And vertical equation gives us that our n plus t sine of theta minus mg is equal to 0. From here we can write that our n is equal to mg minus t sine of theta. Okay. And we can also find out our moment balance about the center, means no rotation basically. We can say that our moment balance about the center, or we can say no rotation. And for that we are having two forces. Suppose this is our center C, and at our P prime we are having a frictional force F, which is at a distance of R, and then we are having a tension T, which is our tangential. So this is tension T and this is our small r. Therefore, for no rotation, we can write that T multiplied by R minus Fr should be equal to 0. Or we can say that our F is equal to R upon capital R times T. But we already know that our F is our T cos of theta. So this comes at T cos of theta is equal to R upon capital R times T. And we can just solve for T, and therefore we get that cos of theta will be equal to R upon capital R. Okay, so it means it is going to remain at rest for this particular relationship. Okay. So we can say for rest, or we can say no rotation, this relationship should hold. It means theta will be cos inverse of R upon this capital R. Now we come to part B. Okay. And we just calculated that for horizontal equilibrium, F is equal to over T cos of theta. Okay. And we also know F is our friction. Okay, so let me write it here. F is nothing but our friction. And we know that the maximum static friction available, maximum static friction available, that is suppose our F max, and it should hold the relationship is equal to mu times n. Okay. And n we already know, n we have already calculated, so we substitute it. Therefore we get that our F max will be equal to our mu, and we have this our mg minus t sine of theta. Okay. And for no sliding condition, okay, we can say for no sliding, we can write, because our F is nothing but our T cos of theta, therefore we can write that our T cos of theta should be our less than equal to mu times mg minus t sine of theta. And we can solve for t or we can say we take t as common, so this comes as t cos of theta plus mu sine of theta is less than equal to mu mg. Or we can write that our t should be less than equal to t max, a particular value of our theta, and that is equal to our mu mg, and that comes our cos of theta plus mu sine of theta. Okay, and we have to remember that this T max theta is the maximum tension, that does not cause sliding. Okay. And this was our B part. Now we come to our C part. So part C, and we already know that our cos of theta is our small r upon capital R. Okay. And from here we can write that our sine of theta will be 1 minus r, and that is our simple trigonometric identity, 1 minus cos square theta. Okay. And we also know that our T max of theta is equal to mu mg, and this comes as our cos of theta plus mu sine of theta. But we want that this T max should be as small as possible. So that is theta dependent. So it means if we are able to maximize the denominator, T max theta will be automatically our minimum. Therefore, we can say that for T max theta to be as small as possible, we maximize denominator. And denominator is our, suppose, d of theta, which is equal to our cos of theta plus mu sine of theta. And we differentiate it, and then we can simply solve the maximum minima conditions. We can say its derivative with respect to theta will be giving us minus sine of theta plus mu cos of theta, and equating equal to 0. Okay. And from here we can say that our tangent of theta is equal to mu. Okay. And for this particular value, we are going to call this theta as our theta naught. Okay. And we got our tangent of theta naught is equal to mu. Therefore, we can write that our sine of theta naught will be equal to mu 1 plus mu square root, and we can write our cos of theta naught is equal to 1 upon 1 plus mu square. And the denominator, our theta naught, we have to remember this theta naught is the maximum theta. Okay. So this comes as our cos of theta naught plus mu sine of theta naught, and we substitute them. we get this as 1 upon 1 plus mu square root plus mu square 1 plus mu square and square root. So this we can write 1 plus mu square and its square root. So it means our, once again, therefore we can say that our T naught, which is our maximum theta T naught, will be equal to mu mg, and this comes as 1 plus mu square upon square root. And we can also find out our R naught now. That was our R naught is equal to R cos of theta naught. So this comes as R upon 1 plus mu square square root. So, and tension, that is our T naught, is our mu mg 1 plus mu square. So these were the 3 questions for today. Thank you.